Okay, so the last method, algebraic method we have is called elimination by addition. And this is really the most useful method, or excuse me, the most general method, one that's guaranteed to work pretty easily and in all cases. And it works, it will generalize to more than two variables or more than two equations quite nicely. So this is really something that I would like us to focus on. But the idea is this. We add maybe appropriate multiples of the two equations together so as to eliminate one of the variables from the resulting equation. Okay, so the two key words here are add. That's the addition aspect of elimination by addition. And eliminate is, we call it elimination because we're getting rid of a variable and getting a new equation which just involves one variable. And what do I want to say about this? Sometimes we'll have to do some manipulation, which is why I put this appropriate multiples in here. But let's just go through a few examples. Goodbye coordinate plane and hello scratchy handwriting from Professor Breck. Alright, so let's see. The first example I have queued up is the following, and this will really exemplify the sorts of things that we are trying to do with the basic process of this method. So I've got negative 2x plus 3y is equal to 7, and my other equation is 2x minus 5y is equal to negative 5. My first step here, I don't have to do any manipulations, so the first step really is to manipulate, but here we're going to skip that. So I'm just going to cross that off because we don't have to do that. The second step is we want to add the two equations together so as to get rid of one of the variables. Well, look, negative 2x and 2x, if we add these sides together, negative 2x and 2x will cancel. 3y and negative 5y will just leave something, and 7 and negative 5 will leave something. So when I add the equations, what I end up with is negative 2x plus 2x disappears, 3y minus 5y leaves me with negative 2y, and 7 minus 5 leaves me with 2. Now I can solve for y, divide both sides by negative 2, and what I end up with is y is equal to 2 divided by 2 is 1, positive divided by negative is negative, so I get y is equal to negative 1. Great, I've solved for y. Now my third step is going to be this thing called back substitution again. And this time it's not as easy as with substitution because we don't have an equation that just says what x is in terms of y. We have equations that involve x and y, and so we're going to have to plug y equal to negative 1 into one of these equations and then solve for x. Which one do I choose? I can choose either, but I'm going to choose the first one because the numbers floating around, at least on y, 3 is smaller than 5, so it'll probably be easier to work with this. So negative 2x plus 3y is 7. Since y is equal to 1, I get negative 2x plus 3 times negative 1 is equal to negative 7, and negative 2x minus 3 is equal to negative 7. I'll add 3 to both sides, which leaves me with negative 2x is equal to negative 4. Let me rewrite this up here. Negative 2x is equal to negative 4. I divide both sides by negative 2, and that gives me x is equal to 4 divided by 2 is 2. Negative divided by negative is positive, so x is 2. And my solution is 2 comma negative 1. That is my final answer. Alright. Well, let's see what happens when we actually do have to manipulate things. So let's solve the following. I'm going to solve 2x plus 3y is equal to negative 10, and 5x minus 6y is equal to 2. Well, the problem here is 2 and 5, when I add them I get 7, 3 and negative 6, when I add them I get negative 3, and so I don't actually eliminate a variable when I add these two equations. But I can multiply either of these equations through by a constant, and that will not change the solutions. Standard form is not unique. If I take standard form and I multiply through or divide through by anything that's non-zero, I get an equivalent equation, which means that it gives me the same line. So first we're going to manipulate. What we would like to do is have the coefficients in front of one of the variables be opposites to each other. Well, 2 and 5, I would have to multiply both of them to make that happen, whereas with 3 and negative 6, if I multiply the top equation by 2, then 3 will become 6. 6 plus negative 6 gives me 0. So we're going to multiply the first guy by 2, and this gives us the new system of equations. 2x times 2 gives me 4x, 3y times 2 gives me plus 6y, and negative 10 times 2 gives me negative 20. And the bottom of the equation is 5x minus 6y is equal to 2. Good, now I've got 6y and negative 6y. So now my second step is to add, and I'm going to solve for the other variable, which is x. So I get 9x, 6y minus 6y gives me 0, negative 20 plus 2 gives me negative 18. So I get 9x is equal to negative 18. I divide both sides by 9, and I get that x is equal to 18 divided by 9 is 2, and negative divided by positive is negative, so x is equal to 2. And my last step is this back substitution step. I can plug negative 2 into any of the equations I have, the first two, or even this new one. Which one do I choose? It's probably best for me to choose the one that has the smallest numbers floating around, and 2 and 3 are smaller than 5 and negative 6. Although negative 10 is bigger than 2 in absolute value, this is probably better because I've got easier numbers to work with on x and y. So I take 2x plus 3y is equal to negative 10, and I plug in x is equal to negative 2, so I get 2 times negative 2 plus 3y is equal to negative 10. 2 times negative 2 is negative 4, plus 3y is equal to negative 10. I add 4 to both sides, and what this leaves me with is 3y is equal to negative 6. I divide both sides by 3, and I get that y is equal to negative 2, and that tells me finally that my solution is, let's time write it as x is equal to negative 2, y is equal to negative 2. Fantastic. Okay. Let's do one more of these, and we'll see that sometimes we actually have to multiply both equations by something to make things cancel out appropriately. So this time let's solve the equation. The equation's 2x plus 5y is equal to 3, and 3x plus 8y is equal to negative 1. So I can't multiply 2 by anything to get 3, or 3 by anything to get 2 unless I introduce fractions. Same thing with 5 and 8. So really, if I want to keep working with whole numbers, I can try multiplying both equations by a number to get the same coefficient in front. But also, all of these numbers are positive, so if I just multiply through by a positive number in either case, I end up with positive numbers, and when I add, things aren't going to cancel out. So when I manipulate, I actually want to multiply one of these equations by a negative number so that I get a negative number on top and a positive one on bottom. So I can either try to get rid of x or get rid of y. Getting rid of y requires me making the coefficients in front of y equal, what's the least common multiple of 5 and 8? 40. I'll get a really big number here. I have to multiply it by big numbers. 8 up here and 5 down here. That's crazy. I'd rather get rid of x because to make the least common multiple of 2 and 3 is 6. So to make the coefficients match up, I multiply the top guy by 3 and the bottom by 2, and that will give me 6's. So let's multiply the top by 2 and the bottom, again, since we want to get some negative numbers down there, let's multiply the bottom by -3. And what does that give us? The top becomes, excuse me, I meant to multiply the top by 3, and the bottom we are multiplying by, instead of -3, we're going to multiply that by -2. Okay, that's what I meant. So the top becomes 6x, 3 times 2x gives me 6x, 3 times 5x gives me plus 15y, and 3 times 3 gives me 9. The bottom equation, 3 times -2 gives me -6x. These will now cancel. 8 times -2 gives me -16y, and -1 times -2 gives me 2. Okay. Now when I add these guys together, what I end up with is 15y minus 16y gives me -y, and that's equal to 9, plus 2 is equal to 11. Okay. Now, this means that y is equal to -11. I can just switch the signs on both sides. Great. Now we back substitute. This was the addition step, sorry. And now we back substitute into one of these original equations. What do we do? Let's back substitute into the one that has smaller numbers floating around. It's probably going to be easier for me to deal with this guy because the numbers are smaller. So I back substitute y is equal to -11 into this first equation, and I get 2x plus 5y is equal to 3. Well, that gives me 2x plus 5 times -11 is equal to 3, or 2x minus 55 is equal to 3. I add 55 to both sides, and I end up with 2x is equal to 58. We're dividing both sides by 2. I end up with x is equal to 29. And this tells me that my solution is -11, 29. Excuse me, the other way around. It's going to be 29, -11, because x comes first, y comes second. And 3 times 2, 27. Okay, I think this works out, but it's always worthwhile for us to check that this works out. 29 and -11. Let's see. We'll check. Our solution was supposed to be 29 and -11, and our original system of equations was 2x plus 5y is equal to 3, and 3x plus 8y is equal to -1. Now, the first equation is definitely right because we got 29 by plugging in -11 in for y, and we solved and got 29. So let's just check with the second equation. We've got 3 times 29 plus 8 times -11 is equal to -1. 3 times 29, I'll let you do the arithmetic yourself, but 3 times 2 gives me 6, 3 times 9 gives me 27, so 60 plus 27 minus 88, is that equal to -1? Yes, that's true. Quickly, if we plug it into the top guy, what do we get? We get 58 minus 55 is equal to 3. Yes, that's true.